Chapter 17, Aqueous Ionic Equilibrium. Now we've discussed this before, the common ion effect. Let's say we have an equilibrium of a weak acid protonating water to form the conjugate base of the weak acid and the hydronium ion. Now if we add a salt that contains the anion A- to this mixture, to this equilibrium, how is the equilibrium going to be shifted? To the left, to the right, or no change? And also, how is this going to change the pH? Is the pH going to be higher, lower, or no different than the pH of the pure acid solution? Turn your playback off, think about it, choose the answers, and come back, we'll discuss it. Okay, so if we add the conjugate base in the form of a salt to the equilibrium, now if you envision our mass action equation, the numerator in the mass action equation grows larger, the value of the mass action equation increases to be a number greater than the equilibrium constant, and the system must respond by shifting in a way to bring down the value of the mass action equation. And it's going to do that by shifting to the left, to make the numerator smaller and the denominator larger. So A- will decrease, hydronium ion will decrease, and weak acid concentration will increase. So this first one, adding the conjugate base salt, shifts the position of the equilibrium to the left. And this causes the pH to be what? Higher, lower, no different? Well, if you're decreasing the acidity of the solution by diminishing the concentration of hydronium ion, the pH is going to be higher. Remember, the higher the pH, the less acidic the solution is. So if we diminish hydronium ion by shifting this equilibrium to the left, the pH is going to be higher than the pH of the pure acid solution. Now, one way of solving for pH is to use the mass action equation, plug in the values of Ka, A-, and Ha, and solve for the hydronium ion. But there's another way as well, and some think it's easier. I personally prefer using just the plain, ordinary mass action equation. But let me give you the Henderson-Hasselbalch equation. If we rearrange and pull the hydronium ion away from the ratio of A- to Ha, and then we take the log of each one of these terms, and then we multiply the log by -1, we get the pKa equals the pH minus the log of the ratio of conjugate base to weak acid. And rearranging, pH equals pKa plus the log of conjugate base anion divided by weak acid. Some like to use this. Me, I prefer to just convert terms so I can use the mass action equation. So here is a question. Use the Henderson equation to calculate the pH of a buffer that is 0.05 molar in this weak acid and 0.15 molar in its conjugate base. So how would you do that? Go ahead and solve for it. If you prefer to use the mass action equation, use that. So here it is, and you would plug in 0.05 for the weak acid. That goes down here. And the conjugate base is going to be 0.15. So it'll be the log of 3, really, plus the pKa that you calculate from the Ka by taking the negative log of it. So if you did all that and plugged them into the Henderson equation, or if you went ahead and solved for a hydronium ion in the mass action equation and converted that to pH, you should have gotten 4.66. So here's an example of the common ion effect at work. Here you have a weak acid reacting with water, forming hydronium ion and the conjugate base. So what do we do to see the common ion effect? We put in some of the conjugate base, the salt of the conjugate base. And what that's going to do is to drive the reaction toward the reagent side. It's going to reduce the amount of A-. It's also going to reduce the amount of hydronium ion. And of course, it's the hydronium ion that controls or is the pH after you take the negative log of it. So just take a look here. This one is pure acetic acid with a pH of 2.9. This one here is pure sodium acetate in water, and its pH is in the basic range of 8.9. You mix the two together and you get a pH somewhere in between with a pH of 4.7. So that's the common ion effect. Here's a table showing various amounts of acetic acid and the acetate ion mixed together, and what the percent of ionization calculates to be and what the pH calculates to be. To practice your skills, we want you to try and come up with these numbers of percent ionization and pH by doing the calculations. You write the reaction equation for acetic acid in water. Then, on the basis of Le Chatelier's principle, explain why the pH rises as the concentration of acetate ion increases. Well, let's try the first line in this, where we have 0.1 molar of acetic acid. We don't have any extra added conjugate base, and we want to calculate the percent ionization and pH to see if they agree with these numbers. So turn the playback off, try it, and come back and we'll do it. All right, well, this is just a weak acid solution. We don't have any extra added conjugate base, acetate. So for this situation, it's 0.1 molar of the weak acid, 0 of hydronium initially, and 0 of the acetate. For change, we say minus X for the weak acid, plus X, and plus X for the products. And then, at equilibrium, we have 0.1 minus X, and we use the X is small approximation because the Ka is very small, and we say that at equilibrium we have 0.1 molar of the weak acid, X of the hydronium, and X of the conjugate base. So X squared divided by 0.1 equals 1.8 times 10 to the minus 5. Solve for X, which is hydronium ion, 0.00134 molar. So the pH is the negative log of that. It comes out to be 2.87. The percent ionization is X divided by the initial amount, 0.1, times 100, which is 1.3%. For the second line in the table, write out the equilibrium expression for the reaction or the Henderson-Hasselbalch equation, and use either equation to plug in the values of the concentration of weak acid and conjugate base of the second line, and see if you can arrive at 0.036 for the percent ionization and 4.44 for the pH. Turn the playback off, try it, and come back. All right, here we go with the Henderson approach to the problem, where the equilibrium constant equals the mass action equation, the concentration of hydronium ion times the concentration of conjugate base divided by the concentration of weak acid. So we rearrange and write the Henderson equation out and plug in our values, 4.74 for the pKa, and then the log of the conjugate base concentration divided by the weak acid concentration. Solving for concentration of hydronium ion, we get 3.63 times 10 to the minus 5, and the percent ionization is therefore that value divided by 0.1 times 100, or 0.036%. Now, if we approach this using the equation and the mass action equation, and avoid the Henderson-Hasselbalch equation approach, we write out the ICE equation, make our approximations to the initial amounts of weak acid and conjugate base, plug those into the mass action equation, and solve for the hydronium ion concentration. And lo and behold, we get hydronium ion concentration of 3.6 times 10 to the minus 5. So the percent ionization becomes that value divided by 0.1 times 100%, or 0.036%. And the pH is the negative log of 3.5 times 10 to the minus 5, or 4.44. Now we need to talk about buffers, which are solutions that resist sharp change in pH when a strong acid or base is added. Many buffers are made by mixing a solution of a weak acid with its conjugate base or a weak base with its conjugate acid. They act when a weak acid or base neutralizes any added strong acid or base to yield more of the weak acid or conjugate base and less of the hydronium ion or hydroxide ion. And after all, it's hydronium and hydroxide that affect the pH. But just like everything else, there's a limit to the pH protection they can afford. So how do you go about making a buffer? You take some weak acid and mix it with its conjugate base, and now you have a reservoir that will neutralize any strong acid or strong base that you add to the solution. So here's a practice problem for you to try. What is the pH of a buffer that is 0.14 molar in hydrofluoric acid with a pKa of 3.15 and a conjugate base concentration of 0.071 molar? Turn your playback off, try it, come back, we'll discuss it. All right, here we go. Here's the Henderson equation. We're simply going to plug in our pKa, and the conjugate base concentration goes in the numerator. The weak acid concentration goes in the denominator. We end up with a pH of 2.86. How'd you do? So the question is, do I use the full ICE analysis or the Henderson-Hasselbalch equation, where you just plug in the initial values? Well, the Henderson equation is generally good enough when the X is small approximation is valid. Generally, the X is small approximation will work when both of the following are true. The initial concentrations of acid and salt are between 1 molar and 0.1 molar, and the equilibrium constant Ka is fairly small, approximately 10 to the minus 4 or smaller. For most problems, this means that the initial acid and salt concentrations should be over 1,000 times larger than the value of the Ka. And in this course, virtually all the problems that we're going to do will allow the X is small approximation. Now, buffers can also be made by mixing a weak base, like ammonia, which has a lone pair of electrons on it, or this generic B with a pair of electrons on it. It's a weak base with a soluble salt of its conjugate acid. And we can also calculate the pH focusing on the equilibrium constant of this weak base. So here's a question. Use the Henderson equation to calculate the pH of a buffer, 0.05 molar in the weak acid form and 0.15 molar in the conjugate base. And we're focusing on the reaction of the conjugate base with water to produce a little bit of the weak acid and hydroxide ion. Now the Kb for this equilibrium is 1.54 times 10 to the minus 10. Changing the Henderson equation to focus on the concentration of hydroxide in the solution, we write POH equals pKb plus the log of conjugate acid divided by weak base. And now we plug in our given information for the Kb, which is 1.54 times 10 to the minus 10. We take the pKb, the negative log of that number, plus the log of the ratio of the conjugate acid divided by the weak base. And when we work it out, we get 4.66. So here's another question. What is the pH of a buffer that is 0.5 molar in ammonia with a pKb of 4.75 and 0.2 molar in ammonium chloride? Here's the equilibrium focusing on ammonia reacting with water to form ammonium ion and hydroxide. Now, instead of using the Henderson equation, we can also approach this by setting up the IRE table and inserting initial concentrations of weak base and conjugate acid. We let X equal the amount of ammonia that reacts and the hydroxide ion that forms. And then, again, instead of using the Henderson equation, we write the mass action equation and determine Kb from the pKb. And we plug values into the mass action equation and solve for X. Here we have to remember that X equals the hydroxide concentration, and if the question is asking for pH, we have to convert that into pH. So turn off your playback, try to do this problem, come back, and we'll talk about it. Okay, so this is how we would do the reaction without the Henderson equation, where we just write the mass action equation. And we take our pKb first off and convert it into the Kb by taking the anti-log of minus 4.75. So the Kb is 1.78 times 10 to the minus 5, a very small number. We do our IRE analysis. Ammonia, we have 0.5 molar initially. Ammonium, 0.2 molar initially. Minus X reacts of the ammonia to form plus X of the ammonia and hydroxide. And then at equilibrium, 0.5 minus X, just about equal to 0.5 because Kb is such a small number. Likewise, 0.2 plus X, and we say it's approximately 0.20, the same as the initial amount for the ammonium ion, and X then for the hydroxide. We write our mass action equation. We plug in the 0.2 for ammonium ion and 0.5 for the ammonia, and we solve for hydroxide, 4.45 times 10 to the minus 5. Turn this into POH, it's 4.35, but remember the question is asking for pH. So don't be one of the students who forgets what the question is asking for, and you select 4.35 as a possible choice because you forgot to convert the hydroxide into hydronium pH, which is 9.65, 14 minus 4.35. Now sometimes instead of asking for pH, a question will ask for the ratio of weak base to conjugate acid or vice versa, what that ratio would be in order to make a buffer with a pH of, in this case, 4.25. And we're given the pKa of 3.74. See if you can do this problem and then come back and we'll discuss it. The equation is weak acid plus water yields hydronium plus conjugate base. We convert first off our pKa of 3.74 into the actual Ka, 1.82 times 10 to the minus 4, by taking the negative anti-log of 3.74. And we do the same with the pH of 4.25. The negative anti-log gives us a hydronium ion concentration of 5.62 times 10 to the minus 5. Now look at our mass action equation over here. All we need do is divide both sides by hydronium ion to cancel hydronium ion concentration on the left side of the equation and divide the Ka by the concentration of hydronium ion. And now we have our ratio that is being asked for in the question, the ratio of conjugate base to weak acid. And to find that ratio, we simply plug in the Ka value that we calculated, divided by the hydronium ion concentration that we calculated, and we get a ratio of 3.24. Now let's try this one. How many grams of sodium acetate, molar mass 98 grams per mole, must be added to 218 milliliters of 0.31 molar acetic acid to make a buffer with a pH of 4.0? And the Ka for acetic acid is 1.8 times 10 to the minus 5. Well, first, find the pH and the pKa and set up the mass action equation with these data, and let X be the necessary molarity of the sodium acetate. Then solve for X, which is the molarity of sodium acetate, and find the needed moles of sodium acetate. If you've got molarity and you've got volume of 218, you should be able to figure out the moles of sodium acetate, and then convert that to grams. Go ahead and see if you can do it, and then we will solve it together. Okay, so here we go. Here is the equilibrium expression, H3O plus times A minus divided by HA equals 1.8 times 10 to the minus 5. The pH is 4, so that is a hydronium ion concentration of 1 times 10 to the minus 4. That's hydronium. And the acetic acid concentration is 0.31. So now we solve for the acetate ion concentration, comes out to be 0.056 molar. 0.056 molar is 0.056 moles of sodium acetate per liter times 0.218 liters. That's from 218 milliliters. So here's our moles of sodium acetate, 0.0122. Multiply that by 98 grams per mole, and we have 1.19 as the number of grams of sodium acetate that has to be added. So what happens is that, let's say you have a buffer made up of the weak acid HA and its conjugate base A-. And let's say you add some sodium hydroxide to this buffer. The first thing that happens is that the weak acid reacts with the hydroxide in a one-way reaction. This is not an equilibrium. This is a one-way reaction, neutralizing the hydroxide, converting it to water, and the conjugate base of the weak acid. So instead of having a lot of excess hydroxide floating around, having a sharp effect on the pH, the hydroxide is neutralized and is replaced by the conjugate base. If you add an acid to this buffer solution, it reacts with the conjugate base and is neutralized by it to form water and the conjugate acid. Essentially, added hydroxide or hydronium ion is replaced by a weak base or a weak acid. And because these do not fully ionize, a sharp change in pH is prevented. We have a little animation to show you. Here's our buffer comprised of the weak acid and its conjugate base. Now let's say I add some strong acid, which has lots of hydronium ion. What's going to happen? It's going to react with the conjugate base, and it's going to get neutralized by it to form more weak acid. The weak acid is going to grow the concentration of the weak acid. Meanwhile, the concentration of conjugate base has diminished. Or, let's say that you add hydroxide to this mixture. It's going to get neutralized by the weak acid, going to be converted to the conjugate base. The conjugate base concentration is going to increase. The weak acid concentration is going to decrease. So that's how buffers work.
And that's all, folks.